Hey all, Dr. Pateki here, back with the final part of the Chapter 8 notes on economic growth and the Solow model. So in this part, we're going to focus on a numerical example and then finish up with the golden rule level of capital per worker. So we'll start right from the beginning and solve this problem. So in this problem, you are given a production function. You are given an aggregate production function. Remember, what do we call this? This specific form here, we call this the Cobb-Douglas form. So in this case, our aggregate production function is big Y is equal to big K to the 1/2 L to the 1/2. Now, since this is constant returns to scale, we know that we can change each of the inputs by a factor. We could divide each of the inputs by a number, and that means we're going to divide the output by the same number. So this implies that we can do big Y divided by L is equal to K divided by L to the 1/2 times L divided by L to the 1/2. So this L divided by L to the 1/2, this just becomes 1 raised to the 1/2. So in other words, the square root of 1 is just 1. So this final term here is just going to disappear. And what we are left with is the aggregate production function Y over L is equal to K over L to the 1/2. And remember, in per worker terms, Y divided by the number of workers. So output divided by the number of workers, we call little y, that's output per worker. K divided by L is capital per worker, that's little k, so little k to the 1/2. So this is going to be our production function for the Solow model in per worker terms. So now notice, because of this constant returns to scale Cobb-Douglas, we can take a little bit of a shortcut here. So whatever exponent is on this k term in the production function, the per worker production function is just going to be y equals little k to whatever this exponent is here, to 1/2. So if this aggregate production function were k to the 1/3 times L to the 1/3, your Cobb-Douglas, or excuse me, your per worker production function would just be little k raised to the 1/3 power. So that's a good good way to double check yourself, or to take a little bit of a shortcut. All right, so instead of solving for the steady state graphically, now the goal here is going to be to examine the steady state analytically. We're going to solve for the numbers and do sort of calculation as opposed to just visualizing it. So in order to do this, we're going to need some numbers. Now we're going to need to make things concrete. So we've already talked about the form of our production function. So this is a concrete form that we can rely on. We're now going to assume that the savings rate is 0.3, so 30% of our income is going to savings and investment. The depreciation rate delta is equal to 0.1, so 10% of our capital stock is wearing out each period. And our initial value of capital is, capital per worker, is going to be 4 units. And so the question is going to be ultimately, what we'd like to know is, what is the steady state capital per worker? Once we figure that out, we should be able to figure out what is the output per worker in steady state, what is consumption per worker in steady state, and what is the investment per worker in steady state. Okay? All we need to do is find K first, and then the rest of the answers are going to flow from that answer. So one way to find the steady state values is to run a bit of a simulation using a spreadsheet. So what we can do is sort of simulate each year out until some arbitrarily large number. Once we get out to a sufficient number of years out into the future, we notice that the values just sort of stay the same. They don't change anymore. Once you get to the point where your values don't change, right? So this says infinity. It actually will stop changing much sooner than infinity. But once we get to the point where these values are steady or stationary, then we call that our steady state, our long run equilibrium. So what we could do is, again, build a spreadsheet, and I've done this on D2L. So there's a spreadsheet template that is something that you can plug in various values of S and delta and initial value of capital and the production function, and you can see how this affects the final answer. So if we were to use this spreadsheet model, just let's run through a couple of these calculations. I think this will help you see where we're getting these numbers from. So the initial value of capital per worker is 4. Okay, so that's by assumption that was given to us. So the initial units of output per worker is 2. All right, so where does that come from? Well, y, remember, is little k to the 1/2 power, or in other words, that's the same as saying that's the square root of little k. Square root of 4 is 2. Okay, so that's our production function giving us this 2. C, where does C come from? Well, the savings rate is 0.3. So we're saving 30% of our income. That means we're consuming 70%, 1 minus 0.3. So 70% of Y is consumption. That's going to be equal to 1.4. 30% of our output, 30% of 2 is 0.6. So our investment is whatever's left over after we consume. Delta K, our depreciation for period 1, for year 1, is 10%, 0.1 times the initial capital per worker of 4. So 0.1 times 4 gives us 0.4 for depreciation. And our delta K, remember our delta K comes from that law of motion for the capital stock. So that central equation for the Solow model that we talked about in the other video. So the delta K is going to be the difference between the investment and depreciation. So investment is greater than depreciation. So that means the capital stock is going to grow. How much is it going to grow by? The difference between these two things. So I minus delta K gives us 0.2. So this is, again, the change in capital stock. So if we go to year 2 now, we can start filling in some of these things. So year 2, right, this is going to be 4. Well, that's what we had in year 1. The net change is going to be 0.2. So this is going to be 4.2 in year 2. So it's going to be the previous value of capital plus the delta K. So now the Y is going to be, I'll do a few calculations here off to the side. So year 2, Y is going to be equal to the square root of 4.2. So the square root of 4.2 is about 2.05. So we can go ahead and plug that in here. So now our consumption is going to be equal to 0.7 times our income, our output, our 2.05. So 0.7 times 2.05 is going to give us 1.435. So that goes over here. And so my calculations might be slightly off compared to the ones below here in the spreadsheet just because of rounding, but it's going to be very close. So that's our C. Our I then is going to be Y minus C. We can do it that way, or we can just do 0.3 times Y, which is 2.05, and that turns out to be 0.615. Our delta K, so that's just going to be 10% multiplied by the 4.2, the capital per worker in year 2. Yikes. Okay, so that's just going to be 0.42. So the delta K then is going to be the difference between the investment I and the delta K. So we just take I minus delta K, which is equal to 0.615 minus 0.42, and that turns out to be about 0.195. All right, so that's year 2. And year 3, we can do something similar. So, battery's getting low. So this spot in year 3 here, so we're going to take the previous capital per worker in period 2, then we're going to see how it changed. So we have a positive number here. This is an addition of 0.195 units. So our capital per worker in year 3 is going to be 4.2 plus 0.195, so we're just going to have 0.395, let's call it. And then similar fashion, we can do the square root of K to get our output, and that turns out to be about 2.1. Consumption turns out to be about 1.47, so that's just 70% of 2.1. 30% of 2.1 is 0.63. Our delta K turns out to be 0.4395, and the difference between 0.63 and 0.4395 is 0.1905. So let's just take a little step back and think about what did we just do here. So, all right, so we started this simulation with some initial values, and then let's see what happens over time. Well, it looks like the capital stock is growing, right? So investment exceeds depreciation. So in year 2, the capital per worker is higher than it was in year 1. Year 3 is higher than year 2, etc. And because of that, because output and therefore consumption is also a function of this capital per worker, little k is going up. That means that y and c and I are going to be increasing as well. So notice, though, that the delta k gets smaller and smaller and smaller as we start to approach steady state. So at first we get a nice little boost in capital per worker, but eventually the change is very, very small until ultimately the delta k gets to be 0. So remember, our steady state, the definition of steady state is when the capital stock is no longer changing, delta k is equal to 0. So the steady state value of capital per worker, and this, for this example, would be 9 units. Steady state income or output, however you want to think about it, is 3 units. Steady state consumption is 2.1, and steady state investment is 0.9 units. Now the spreadsheet that I have on D2L for you has a little area where you can play around with the depreciation rate and the savings rate and things like that, so you can see how the steady state values at the bottom change when you change any of those model parameters. And so it should match up with your intuition that you had from that graphical analysis. Right? So the graphical analysis said that when the savings rate went up, the steady state capital per worker went up. So if we were to change 0.3 to something like 0.5 up here in our initial conditions, we would expect to see, in the long run, we'd expect to see higher capital per worker and higher output. All right, and if you don't have a spreadsheet all programmed nice and handy, then we can solve for this algebraically without too much trouble. So again, we're going to be given the same initial conditions here. And this time what we're going to do, instead of using a spreadsheet like that, we're going to use the equation of motion, what I've been calling the law of motion, equation of motion, so same thing. We're going to use this equation here to solve for the steady state values of capital per worker, output per worker, and consumption per worker. So in order to do that, let's just write down some things that we know here. So, let's change to marker. So delta K, our law of motion, says that the change in capital is going to be equal to S times F of K, which is our investment, minus our delta K, which is our depreciation. So we know that in steady state, key piece of information we need to know is that delta K is equal to 0. So once we know that, this is our steady state condition, we can take delta K is equal to 0. We can just plug in 0 into our equation of motion here. And then this is going to give us an equation in one variable that we can solve for. So let's do that. Let's just set the equation of motion 0 is equal to S times F of K minus delta K, right? So we also know that the production function F of little k is equal to K to the 1/2, right? So that, again, that was given in the problem. So we can say that S is 0 is equal to S times little k to the 1/2 minus delta K. So now we have an equation with one variable, little k. We have a couple of parameters here, s and delta, but remember these are just determined elsewhere. These are numbers that are given to us in the problem. So we have one equation with one variable. That means we can solve for that one variable. So we just have to do a little bit of algebra here to solve for little k. So the first thing we can do is add delta k to both sides to start the process of solving this thing. So if we add delta k to both sides, we're left with delta k is equal to s times k to the 1/2. And I always like to have the variable I'm solving for on the left-hand side. So in this case, what I'm going to do is in order to isolate k, get k on just one side, I'm going to divide both sides by little k to the 1/2. Okay, so those terms are just equal to 1, so those go away on the right-hand side. So we're left with delta k divided by k to the 1/2 power. So now remember our rules of exponents. K is the same as k to the first power. So when we're dividing a variable that's raised to exponents like this is the same as saying delta times k to the 1 minus 1/2 power, right? So if we're dividing terms like this, we have to subtract the exponents. So now this is equal to s. So k to the 1 minus 1/2 is equal to delta k to the 1/2 is equal to s. We can divide both sides by delta. Right, so this goes away, and so I'm just going to continue this over here. So we are now at the point where we have k to the 1/2 is equal to s divided by delta. So now, some of you may be wondering, how do we get rid of this exponent? So again, remember our rules of exponents. If we have a variable raised to an exponent and we raise that whole thing to another exponent, we multiply the exponents. So the goal is to turn this 1/2 into a 1 somehow. So in order to do that, we know we need to raise k to the 1/2 to the second power. So when we multiply 2 times 1/2, we end up with, let me just keep this, s divided by delta here. So when we multiply 2 times 1/2, we end up with k to the 1/2 times 2 is equal to s divided by delta. And we've squared the left-hand side, so we also need to square the right-hand side, s over delta squared. So on the left-hand side, 2 times 1/2 is just 1, so then we're left with little k to the 1 power is equal to s divided by delta squared. So k to the 1 is the same as k. So remember, we're talking about steady state, so we put a little star here. So the steady state value of capital per worker is equal to s divided by delta squared. And so we know we were given these values in the beginning. So s is equal to 0.3 and delta is equal to 0.1. So we can plug those things in. So that's 0.3 divided by 0.1 squared. 0.3 divided by 0.1 is 3. 3 squared is equal to 9. That's the same exact thing that we got before. So now we can go back and figure out, so if little k star is equal to 9, y star is equal to 9 to the 1/2 power, which is square root of 9, which is equal to 3. Consumption per worker in steady state is equal to 1 minus s times little y, which is equal to 0.7 times 3, which is equal to 2.1. That's exactly what we found in the other spreadsheet version. So investments, whatever is left over, this is going to be I star is equal to y star minus c star, which is equal to 3 minus 2.1, which is equal to 0.9. So now we have solved for all of the important variables in this model, purely using algebra. And we should be able to get some intuition by looking. Let's go back to this expression right here. So the steady state value of the capital stock per worker is S divided by delta squared. So we automatically know just by looking at this that if S goes up, this fraction is going to get bigger, and since we're squaring it, if the fraction gets bigger, then K star is going to get bigger. If delta goes up, all else equal, then the fraction is going to get smaller. For squaring a smaller number, then K star is going to decrease. So we get some pretty nice intuition here just from using a little bit of algebra. Your favorite, right? From Math 181. Well, see, it was useful after all. So let's suppose that our savings rate, our S1 is equal to 0.3 like we had previously, and this is going to increase to a second savings rate, S2, that is equal to 0.4. So we go from saving 30% of our income to 40%. How does this affect the capital stock per worker in steady state? Okay, so we can do this a couple of different ways. We can solve this exactly by using the algebra we just looked at, but I also want to quickly draw the diagram to show you how these two things match up. So we know that K star is equal to S divided by delta squared. Okay, so again, we are still assuming that y is equal to little k to the 1/2. So if we change our production function, that exponent, that is not going to be squared anymore. We're going to have to be mindful of that exponent. But for that production function, we just figured out that K star is equal to S divided by delta squared. So the initial steady state, let's call this K star 1, was equal to 0.3 divided by 0.1, which is 3 squared, which is equal to 9. K star 2 would be equal to 0.4 divided by 0.1 squared, which is just going to be equal to 4 squared, which is equal to 16. So increases in the savings rate caused the steady state capital stock to go from 9 to 16. It increases, just like we'd suspect with the savings rate. Again, let's go back to the diagram real quickly here. Should be able to draw this thing out pretty quickly now. So this is S times F of K. This is delta K, so we have our depreciation function and our investment function. Here's our initial K star 1, and so with a higher savings rate, this investment function is going to shift up like this. So this is S2 times F of K. And we see that this increases, right? So this was 9 and this was 16. So the diagram, the algebra, this should all match up and it should all make intuitive sense. So since we know that different values of S, different savings rate, lead to different steady states, what is the optimal savings rate? How do we find that? So one way to define the optimal savings rate is the one that gives us the highest consumption per worker in steady state, the biggest C star. So ultimately that's the goal, right, is to have as many goods and services as we can per person. That's our standard of living. So if our goal is to maximize the standard of living in steady state and equilibrium, then this is what we should do. We should try to make C star as big as possible. So when we change S, there are two things that are working against each other. So a higher S means that we have more investment and more capital per worker in steady state. More capital means more output according to our production function. So more output means more consumption. However, when we raise S, right, we're saving more and consuming less, which means that's going to tend to lower our consumption in steady state. So we have these two opposing forces. How do we find the value of S that leads to the value of K that leads to the biggest value of C in steady state? So the rule that gets us to this maximized C star is called the golden rule. So a little bit of notation here. So this K star gold is the particular steady state capital stock that leads us to this optimal level of consumption. So we're going to call this K star gold as the golden rule level of capital. So in order to find this maximized level of consumption per worker, we're going to go right back to one of the initial equations we talked about in this model, the national income identity. So Y is equal to C plus I. In other words, there's only two things we can do with Y. We can either consume it or we can invest it in this model. So we're just going to do a little bit of rearranging. If we isolate C, and let me move it over to the left-hand side. So just again rearranging this first equation, we can say that C star is equal to Y star minus I star. So now we want to see how C star is related to K star, so we need to do some substitution here. So we can say that Y star is given by the production function. So remember, the production function depends only on K star. So let's sub in f of K star for Y star. So that leaves us with C star is equal to f of K star minus I star. So now let's work on the second term here. So we know that in steady state, the forces of investment and depreciation just balance each other out. In other words, investment is equal to delta K. So that allows us to sub in delta K for I over here. So now what we're left with is C star is equal to f of K star minus delta K. I'm not going to ask you to do this, but we could use calculus pretty easily to find the value of K that maximizes C. So using function notation, let's just say that we have this function C of K is equal to K to the 1/2, that's our production function, minus delta K. So remember, the way to maximize, to find a local maximum, if you remember from business 281, what we should do is take the first derivative, C prime, and so what we would do is set that equal to 0. So what that amounts to is taking the first derivative of this right-hand side, setting it equal to 0, and seeing where that takes us. But again, I'm not going to ask you to do that, but that's where the math comes from. We can do this same sort of thing graphically, though, and that's what we're going to do on the next slide. So if we are to find the golden rule level of capital per worker graphically, so this simply amounts to looking at that graph we looked at a little bit earlier, where we say on the x-axis we are looking at all the potential values of K star. So these are all of the potential values of the steady state capital per worker. And so we're going to try to find the value for K star along this x-axis that makes our consumption per worker the biggest. So remember, consumption is going to be the difference between the production function, which is this green line, and the investment function, which is this sort of magenta, red, whatever that is, line. So in other words, this gap between the green and the red line is biggest where our golden rule level of capital is. And so it turns out that there's this rule of equal slopes here that suggests that the point where C is maximized, the slope of this production function is going to be equal to the slope of this depreciation line. And so the slope of the production function, remember that we have a name for that, we call that the marginal product of capital. The slope of this depreciation function is just going to be delta. And so the K star gold is going to be the point where the marginal product of capital is equal to the rate of depreciation. And that's our that turns out to be our golden rule. And so this diagram just cleans up the presentation a little bit. So if we just simply look at our production function and our depreciation line, we can see that, again, we're looking for the biggest gap here. So our golden rule level of capital is going to be the point where the slope of the production function is equal to the slope of the depreciation line, and that's going to be where the marginal product of capital is equal to delta. And if we know the production function, we can come up with an expression for the MPK. We can figure out exactly what this is. Delta is just some number that's given in the problem, so we can actually solve for the golden rule level of capital that maximizes consumption by using this little formula here. So I don't want you to get too caught up in the golden rule stuff here, but I do want you to know that there is a particular savings rate that will maximize consumption, but it is important to know that the economy does not have a natural tendency to move towards this golden rule. So this is not like an equilibrium condition that, the model's going to sort of gravitate towards over time. So this actually requires policymakers to adjust the savings rate. So providing incentives to people to save more or save less by changing their fiscal policy to collect more taxes or fewer taxes or increase spending or decrease spending. So all of those things will affect the rate of savings in the economy. So if we determine that our capital stock is too low, then we should increase S, provide incentives for people to save more. If we find out that we have too much capital, then we should do the opposite. But if you actually do this sort of analysis and look at the capital stocks in various economies around the world, you'll notice that most of them are below the golden rule level. So it's not very common for an economy to have too much capital. It can happen, certainly, but generally speaking, economies are going to be better off if they save a little bit more. So it's interesting to look at what happens to all of these different variables as we transition from one steady state to the next. So let's say policymakers are able to identify the golden rule level of capital and they create incentives to get us there. What is that going to look like? To analyze the dynamics of a macroeconomic model, we use a very common type of graphical representation. So we call these sorts of things an impulse response function. So basically this is just a time series sort of graph that shows over time what happens to the variables in the model when something happens, right? Something changes or there's some stimulus. In this case, we're changing the savings rate in the model and we're seeing what happens to output, consumption, and investment. And so again, this is the sort of hypothetical scenario where we have too much capital. So our current steady state is greater than the golden rule steady state level of capital. So it's not common, but it's possible. So this essentially means we have too much capital, so we're saving too much. So if we save a little bit less, we can increase our consumption in the long run. So let's see what happens to these variables over time when we throw a little wrench into this model here. So think of this as our starting point. So this is T0. T stands for time. So let's say at time 0, something happens, right? So the savings rate falls at time 0. So immediately consumption shoots up, right? So if we're saving less, we're consuming more. So at time 0, when savings goes down, investment goes down as well. So consumption goes up and investment goes down. Those things are mirror images of one another. So investment goes down by the same amount that consumption goes up because y has not changed at t equals 0. So that first period, we're just figuring out a different way to divide up what we're going to do with our output. But then as time starts to roll on, so period 1, 2, 3, 4, etc., these variables are going to evolve, right? So since we are investing less, that's going to mean that we are going to end up with a shrinking capital stock, right? Because capital's wearing out and we're not replacing it as quickly. So that's going to reduce capital. So lower capital means that we are going to have a decreasing output, because output is a function of how much capital we have in this model, capital per worker. So as output shrinks, so too does consumption, because consumption is just a fraction, a constant fraction of output. So as y gets smaller, consumption gets smaller. Likewise, as y is getting smaller over time, we have less to consume and invest. So investment's going to be getting smaller as well, just a little bit though, because consumption's getting smaller. So that does leave a little bit more left over for investment. So this change here isn't quite as dramatic as the change in C. So one thing to notice here is that so we have this big boost in consumption initially. So this is awesome, right? So policymakers say, hey, we need to save less. Woohoo, right? We get to consume a bunch more in the first period. Well, this leads to lower output over time, but notice that our consumption permanently stays higher than it was in our baseline. So it's higher than the dotted line, and that's where we started. So by saving less, we end up in the long run with a level of consumption that's higher than it was initially. So that's a net improvement to the standard of living. The more common situation, though, is starting with too little capital. So if the current steady state is less than the golden rule level, then if we want to maximize C, that means we need to save more so we can invest more and thereby increasing the capital stock. So basically what this means is there's going to have to be a sacrifice initially. So future generations, your kids will be better off, but you are going to have to sacrifice in the short term. And so again, so at T0 now, instead of decreasing savings, we're going to increase savings. So when that policy change goes into effect, consumption drops immediately. Since Y doesn't change immediately, we're just dividing up C and dividing up Y between C and I differently. I is going to increase by the same amount that C decreases. So consumption decreases initially, but that allows us to invest more. That higher level investment leads to more capital, which pushes output higher and higher. So as output increases, we can both consume more and invest more. And so again, this leads to a level of consumption in the long run that exceeds the baseline, this dotted line where we started. So there was some sacrifice initially, but that savings led to higher capital and increasing output and consumption. And with that, that about wraps up Chapter 8. So there's a lot of material there, I know. So please let me know if you have any additional questions. I can always help you one-on-one or create another video. So whatever's going to help you guys, I'm here for it. So just let me know what you need.